Let's understand what is a common emitter characteristic for an NPN transistor. Alright, now look at this particular circuit. Now first, let's try to understand the circuit. You have a transistor, correct? And next to a transistor, if you look at the emitter and base, okay, emitter and base. See, we call it as a common emitter configuration because emitter is the common part for both base and the collector. See, generally base is the one which is connecting all of them, both of them, correct? Emitter and the collector. Now, emitter is the common part. That's why we call it as CE configuration or CE characteristic. Now, in this one, first thing what you have, if you look at the base emitter, that part of it, what you are going to have a forward biased condition. And connected to that, we have VBB, that's the potential, and you have RB, the input resistance. In the sense, input in the sense, remember it's like a rheostat types. Then we have the microammeter and you have the voltmeter. So VBE. So VBE gives you the input voltage. Okay, and the IB, whatever is being passed through the base, that is measured by the microammeter. Fair enough. And if you look at the collector side of it, collector emitter side of it, here you have 1 milliammeter, because generally milliammeter we use it for collectors because the current is more. Second, you have VCE. VCE gives the output voltage. In the sense, as you keep on changing VBE, how VCE is going to change, you have to see it. Alright. Then that is connected to VCC, which has to be under reverse biased condition. This is the entire circuit. And you know that IE is equal to IB plus IC. So obviously the current is going to split in the same way. Now that you have the circuit idea as to what is happening here, there are two things. One is called as the input characteristic. Another one is called the output characteristic. Okay, now in input characteristic, what we do is we keep the output parts constant. In the sense, VCE and IC, not IC, VCE. VCE we try to keep it constant. Then we start to change the value of VBE. In the sense, see, you have that VBB, correct? You keep on changing the value of VBB and you see how the VBE, IB and VCE are changing. Okay, how it is changing? In the sense, you try to change VBE and see what output do we get in VCE. Okay, this is what we mean by input characteristic. So for that, look at this particular graph. Now what you have a VBE and you have IB. And you see the graph and we have a slope and everything, correct? Now when you have a VI graph, we can calculate the resistance, isn't it? We are going to do that at the end of this input characteristic. So what are the observations and conclusions we can get from this particular graph? First conclusion or observation is that, see, IB is very small as long as VBE is less than a particular potential barrier. Okay, less than that one particular barrier. Now second one is, suppose if VBE becomes more than the potential barrier, then the current increases rapidly. You guys can see that in the graph, isn't it? See, it's like an exponential increase in the current. See, the next one is, suppose if I keep VBE constant. Okay, if VBE is kept constant, then IB decreases if VCE is increased. Alright, now based on all these things, we have dynamic resistance for the transistor, or what we call as the dynamic input resistor for the transistor. Okay, now that can be calculated with the help of, see, Ri. Ri is in the sense resistance of the input characteristic. Ri is equal to delta VBE divided by delta IB, where VCE is kept constant. Fair enough? This is basically the dynamic resistance, because obviously you guys can see from the graph it's not the same, and we calculate the slope for that reason itself. At that moment, at that instant, what is the dynamic resistance? Now let's try to do the output characteristic. See, output in the sense what? You keep the input part constant and you see how the output is going to change. Correct? So we change in VCE, keeping IB is constant. Or you can say that, we are going to keep IB constant. Look at this particular graph. If you look at the graph, what do you see? Again, you are going to see the x-axis, y-axis. See the legend what we have around the x-axis and y-axis. Okay. Now, what conclusion and observations we can do with the help of this particular graph? The output characteristic, to be very, very precise. See, in output characteristic, what we have is that, see, VCE is going to increase, provided IB has to be kept constant. Okay. VCE keeps on increasing. IC also keeps on increasing. Now, both of them increase, correct? Now that you have that particular value, right? That voltage is called as knee voltage. Okay, knee voltage plays a very, very important part. Suppose if VCE becomes more than VBE, assume. Okay, because you can change the value, right? Suppose if VCE becomes more than VBE, then the junction becomes reverse biased. So, IC value starts to change linearly. Okay, it's a slow growth, but it's going to be a linear growth. Now, the third observation what you can do is that for a given value of VC, the value VC, the output voltage, IC is going to be greater if IB value becomes more. Okay, in the sense as IB keeps on increasing, IC keeps also increasing. Okay, now you have the output resistance, correct? Or you can say the dynamic transistor resistance. For that, we can say R0. Actually, it's R output. That's why we write it as RO. Okay, so RO is equal to delta VCE divided by delta IC, provided IB is kept constant. Okay. Now, in a transistor, there are three important regions what you have to understand. See, those three regions, we have saturation region, cutoff region, active region. Okay, now to understand this one, again look at this particular graph. You see the left side, that OA part, the shaded part, that is what we call as the saturation region. See, in this saturation region, VCE is less than VBE. Okay, that's why this region is called as the saturation region. The second type of region, the cutoff region. See, in cutoff region, both the junctions, whatever you have, both of them are reverse biased. In the sense, IB and IC, both of them will be 0. See, this region is very important to us because transistors in this region, we can use transistors who are in this particular region as switches. We can use them as switches, for switching on and off the circuit. You will understand how transistors can be used as a switch in the next upcoming videos. Okay, so switches, transformers as switches, there we are using the cutoff region. The third one is the active region. See, active region is between that. Okay, see, on the leftmost you have the saturation, on the bottommost you have the cutoff, in between you see, right? That is what we call as the active region. See, in active region what happens? Transformers behaves in a normal particular fashion, in the sense the emitter base junction is forward biased, collector base junction is reverse biased, and the current flows normally, properly. Now, in this state, the transistor can be used as an amplifier. Okay, again, this also amplifier. You are going to understand this in the upcoming videos. Alright. So, in CE characteristic, what all did we do? We learnt about the input characteristics, correct? We have the graph. And in input characteristic, you are going to keep VCE constant and you are going to change the value of VBE, however you feel necessary. And you have certain points and observations to note. And in the output characteristic of the same CE configuration, we keep the input constant and we change the value of VCE and we figure out what are the values. Correct? So these two are going to give us how a CE configuration of an NPN transistor is going to behave. Now that we understand the behavior, let's see certain applications of transistor in which you are going to learn about one or two of them. One is switch one is an amplifier, and one of them is an oscillator. Okay, so these are the three applications what you have for the transistor, which you will learn in the next videos.